Robin's criterion and the Riemann hypothesis, narrated by the author Valentin Bura. I dedicate this exposition to Dr. William Babe, an important person, an important New Zealander, and a great medical doctor, a person who has given his life protecting the life of others, including my life. I am grateful to the late Bill Babe. Hello, this is Valentin Bura, and I have proved previously the collapse of the polynomial hierarchy. A great result in itself. That particular proof is on archive. It's a paper. The paper is called Positive 1 in 3 set admits a non-trivial kernel. It is on archive. You may find it under my name. An awesome result, hence the poetic style of the paper, as nobody thought that the polynomial hierarchy would indeed collapse. So for that paper, be prepared to be shocked a little bit. Okay? Right now, I'm going to run you through my proposed proof for the Riemann hypothesis. Yes, the Riemann hypothesis, probably the greatest unsolved problem in mathematics in the last 200 years or so. So, yeah, bear with me on this one. Thank you. Let's get to work. The Riemann hypothesis. A problem proposed by Bernard Riemann, as the name suggests, of course, a very, very long time ago. Arguably the most important problem in mathematics today, if I'm not mistaken. The status of this conjecture is open. Srinivasa Ramanujan has done a lot of work, yes, of course, Ramanujan and Hardy, yes, at Cambridge, beginning of the 20th century. I think Paul Erdős did some work on it. Erdős was a keen number theorist. What we are going to focus on in this approach is a paper by Robin, published in 1982, I think, which sort of elaborates a little bit on the results of Srinivasa Ramanujan. A matter of notation, we write very simply the following identity. Phi of n equals e to the gamma n log n. So, phi of n is e to the gamma n double logarithm of n. Phi is a function, of course, it's a function on the positive integers. E in this context is the base of the natural logarithm. Gamma is Euler's constant. We will take it as defined by Robin. I'm not going to explicitly write it here. This is not the course in mathematical analysis as such. The proof itself does not make much use of mathematical analysis. It's basically a combinatorics proof. Technically speaking, I work in computer science and in combinatorics and optimization. Phi of n here for a complex expression. The paper makes use of this technique, well, it is syntactic sugar really, to simplify things. So we write symbolically phi of n for this particular expression, e to the gamma n double logarithm of n. If you know about Łukasiewicz and Łukasiewicz logic, you can see it's kind of similar. So we make use of that in order to simplify notation a little bit. I hope you will enjoy this in the paper itself. We also write sigma n to denote the sum of divisors function. So Sigma n, that's standard notation in number theory, elementary number theory. The sum of divisors function. Example. So, okay, sigma 4 equals 7. This is because 1 plus 2 plus 4 equals 7. So 1 divides 4, 2 divides 4, and 4 divides 4. So therefore, sigma 4 equals 7, 1, 2, and 4 being the divisors of 4. Sigma 5 equals 6. This is because 1 plus 5 equals 6. Yes, 5 is a prime number. Sigma 6 equals 12 similarly. It is, as the name implies, the sum of all divisors of the positive integer n. So that's what sigma n is. Notice that this is fluctuating actually. It's not strictly increasing or, okay, strictly decreasing, but it's fluctuating, so it can take very high values and then come to a low when we reach a prime number, and then it can go up again. Very neat way of making an account of the prime numbers in the positive integers. Robin's criterion. 1982, Robin proves that this problem, this conjecture, the Riemann hypothesis, holds if and only if sigma n is less than phi n for a finite number of values of the positive integer variable n. To restate this, if sigma n is greater than phi n for infinitely many n, then the Riemann hypothesis fails. But I've given you the hold condition here. So sigma n must be less than phi n for a finite number of values of the positive integer variable n. We show here this is in fact the case, that sigma n is indeed less than phi n for only a finite number of values of the variable n. There are a bunch of values for sigma that do not verify the claim. They start at 2 and they finish at 5040. Just a handful. These are the cases that do not verify the claim. A key observation here is that all of the previously stated values, the values that do not verify Robin's criterion, are a combination of the following form. It's a product, so it's 2 to the a times 3 to the b times 5 to the c times 7 to the d, for values of a, b, c, d that are bounded above and in fact extremely small. So we prove here Robin's criterion fails for positive integers that are necessarily smaller than the following threshold. And it's, okay, 2 to the 5 times 3 to the 3 times 5 to the 3 times 7 to the 2. Okay, this is probably higher than necessary. A computer search shows that the numbers stated before, the numbers that begin at 2 and end at 5040, are the only ones that fail Robin's criterion. This is a technical condition, and this is the bound. We prove in our paper that any positive integer that is greater than this threshold must necessarily satisfy Robin's criteria. Now, another key observation. When we think about the natural numbers or the positive integers, we think about counting, right? 1, 2, 3, 4. So it's the natural order induced by counting or by the successor operation that maps n to its successor, n plus 1. That's what we have in mind when we think about the natural order on the integers. And pictorially speaking, this is what happens if we compare sigma to phi using the natural order on the integers. This is the picture. So we can see a function, it's clearly growing, but it's fluctuating, and really nobody knows, or nobody has really proved Robin's criterion in fact holds for all of the numbers above a certain threshold. Hence, the Riemann hypothesis is open. In this particular case, in this particular instance, we must think outside the box. We must find a different order on the positive integer numbers. The natural order on the integers is a little bit misleading here. We are going to use a result that most of us are familiar with, the unique factorization theorem. This says that every integer greater than 1 is either a prime number itself, or it can be expressed as a product of prime numbers, and this representation is unique. Okay, so this is a technical requirement, a very fortunate theorem, and this induces a special order on the positive integers, on the natural numbers. This order is a partial order on the positive integers induced by each integer's prime factorization. And the order looks like that. It is a partial order. And it's very, very good news. Extremely good news, because this allows for a mathematical induction on a thing called structure of the integer factorization. So we can basically do an induction on this partial order. Really, that's not a new concept that as such, because I've met that before personally in model logic, in Creswell and Hughes. In logic, yes, it's very common in logic, induction on structure, basically, but I'm applying it to the factorization of the positive integers. That's all there is to this, if we want to keep it in a nutshell. Pretty much. That's all there is to this. If you have some level of expertise in elementary number theory, you will see this is pretty much correct. You will understand where this is going. There's no need for elliptic curves and Duval's kind of stuff. This is really just elementary number theory and case analysis. It's combinatorics, really. If you know a little bit about elementary number theory, you will see where this is going. You will see, otherwise it would be just like David Beckham missing a penalty kick, which didn't really happen very often. So yeah, it's like that a lot. Okay, so you may want to check my 2 papers. Well, I have more than 2 papers. I've contributed a lot in the past. So the 2 papers, the first one about the collapse of the polynomial hierarchy. And this paper is called On Sum of Divisor and Robin's Theorem. It is on Academia, it is on ResearchGate, it is on my personal website, valentinbura.online. And a few acknowledgements. I need to thank Noam Greenberg, my academic advisor in Wellington. Noam is an excellent mathematician. I've learned a lot from him. I can say that we've collaborated well. And I need to thank the people at my mother's place of work in Subiaco, as my mother has financed most of my research in the past and my graduate studies. Thank you very much for your attention on this. After this rather long abstract or rather long summarization of our results, let us go through the paper in a somewhat more in-depth fashion so that there can be no misunderstanding of what we have proved here. There can be no objection and there can be no statement that our work, our proof is in fact not accurate. So let me run you through in a more in-depth fashion through our results. The paper is split in several sections. Let's begin with the preliminaries, as we have already covered a little bit of the background in, say, elementary number theory. There are a few facts from mathematical analysis that we make use of. Namely, for a finite series of the form 1 plus r squared plus and so on to r to the n, we make use of the formula for the summation in question, which is given here. So we take this as a fact. All right, the function we also take as a fact that the function f of n equals q minus 1 over n for any constant q converges asymptotically to q, since we have the following. So we do give an argument for this fact. Therefore, any such function will converge asymptotically to q when n tends to infinity, of course. This is the meaning of asymptotical convergence. And there exists quite an established field in a subfield of mathematical analysis that deals with asymptotical convergence of functions. Similarly, we also take as a fact that the function g of n equals log n is increasing. So g of n equals double logarithm of n is strictly increasing. And again, this is taken as an established known result, so we don't get into the details. The first remark we are concerned with is remark 1 in our paper, the unique factorization theorem, which states every integer greater than 1 is either a prime number itself or can be represented as the product of prime numbers, and this representation is unique up to the order of factors. In effect, what this says is that any integer whatsoever that's greater than 1, so any natural number as we know them, can be written as a product of prime numbers. That's all that remark 1 says. And in the case that the integer in question is a prime number itself, then this product is just the number itself. So it's a technical requirement and we do make use of it. It's proof. It is a well-known result in mathematics, and its proof is simple, I'd say. I'd go about proving this statement by obviously assuming that the integer in question has a factorization, and then breaking down this factorization into subfactorizations, and in the end we reach. We shall reach a prime number. So this particular statement is rather obvious to me. So I'm not again, we take it as granted for the sake of running quickly through our results. We don't provide a proof for this, but the proof is left as an exercise to the keen reader. So assuming remark 1, we let P of n be the nth prime, and for any natural number m, we commence with its compact factorization into primes, which looks like that. M equals P1 to the power of A1, and so on and so forth, to PS to the power of AS. So there's P1, P2, and so on to PS primes, and they are raised to the power of A1, A2, and so on to AS. This factorization into primes is compact, as I have said. It has the extended form M equals B1 times B2 times B3 times and so on and so forth to BK, where each BI is a prime. And it's not necessarily distinct. We also give the relationship between the two types of factorization, the compact one and the extended one. Yeah, that is the relationship between them. It's stated right there at the bottom. And okay, it's important to note well of both of them. These two facts, these two algebraic facts, if you want, about the natural numbers are very, very important in our proof, and we shall in our proof, in what follows, we shall make use of both of them, and we shall switch from one representation to another and vice versa in order to perform an induction on the natural numbers according to some non-standard ordering. Going further, we define sigma of M as the sum over the divisors of M. So is the sum of divisors functions. We have already explained in our summary what this function is. So we'll just leave it at that. Capital omega. We define the constant capital omega as 2 to the 5 times 3 to the 3 times 5 to the 3 times 7 to the 2. We've already explained in our summary what this is all about. It is a threshold, and in what follows we shall prove that any number exceeding this threshold satisfies Robin's criterion. We define the constant delta using the values provided by Robin for gamma and e to the gamma. The values are stated here. So we have a real value for gamma. This is a real number, and we have a real value for e to the gamma. They represent both of these constants being infinite in representation. Now we define delta as 1781 to the power times 10 to the power of minus 3. And we note that in remark 5, we note that delta times x is less than e to the gamma times x for any x real with x greater than 0. Hence, we make use of this rational number. So delta is a rational number for our proof because, this rational constant delta bounds. The product of any real x times multiplied by this rational constant delta bounds below the function e to the gamma times x. So it is a rather convenient way of basically delegating, if you want some terminology from software engineering. We delegate this this problem, the problem of the problem that e to the gamma is in fact infinite in representation, problem to solving a simpler problem by identifying rational threshold that's always lower than e to the gamma times x. And that's about it. That's what remark 5 is all about. We define function phi phi of m. So there's two versions in LaTeX for phi. We define rounded phi as delta times m times double logarithm of m, and we define the standard phi as delta times double logarithm of m. And we note that standard phi of m is equal to rounded phi of m over m. So this is just a matter of notation. I've already drawn your attention to Łukasiewicz's technique of reasoning symbolically from a bunch of primitives, and we do make use of this of his technique in order to simplify things. Now we define maps tau and xi, that's the Greek letter xi or x. Now tau itself is a function of two variables, where so we define tau of p and a, where p is any prime, so and a is a natural number. So tau of p and a is the sum. It's simply the sum p to the 0 plus p to the 1 plus p to the 2 plus and so on and so forth plus p to the a. That is the definition of tau of PA. We define xi, and we define xi starting from so we define xi of m starting from the representation of m, the compact representation of m into factors. Again, m is a natural number, so we define xi of PA as before, except as in the definition of tau of PA, except that each term is inversed. So explicitly, xi of PA is 1 over p to the 0 plus 1 over p plus 1 over p to the power of 2 plus and so on and so forth plus 1 over p to the power of a. And we define xi of m. So we define these two functions, tau and xi. Definition 10, a technical requirement. This definition is given very early, just so that we give the reader the chance to understand. We give some transparency to our proof. So we let m be a multiple of a prime b. So basically, m equals b to the a for a given prime b, and we define alpha of m as follows: alpha of m equals b to the powers of 5, that's when b equals 2. Alpha of m equals b to the power of 3 for b equals 3. Alpha of m equals b to the power of 3 for b equals 5. And alpha of m equals b squared for b equals 7. And alpha of m equals b for b greater or equal to 11. Now what this is a map or a function. We use the terminology map and function interchangeably. What this is a map that maps certain powers of primes to natural numbers. That's all there is. And in definition 11, we let m be a power of a prime, and we let beta of m, again a map, beta of m be m divided by alpha of m. So, okay, basic algebra, in effect, this is just simplifying symbolically. It's symbolic algebraic simplification of the types of equations that we study. Moving further, we still remember we're still in the let's say preamble of our paper. Remark 12 and remark 13. Okay. In 1982, Robin shows the Riemann hypothesis implies that the sum of divisors function is less than that expression for all n greater than 5041. And again, remark 13, if the Riemann hypothesis fails, then the sum of divisors function is greater than that expression, the same expression, e to the gamma m double logarithm of m. We show here, as we have stated in the summary, we show this is not the case. We show the condition in the remark 12 holds. In effect, what we managed to show through an implication, through the link in the chain that belongs to Robin, we are able to show that the Riemann hypothesis stands. This is very important. This point, the point that I'm going to make now, is probably characterizing our. It's a concise characterization of our proof and our methodology. So basically, for n less than 5041, this integer starting at 2, ending at 5040. Fail Robin's criterion. And this happens for certain combinations of the following exponents. So I've given you some values for A1, A2, A3, and A4. And, okay, for certain combination of these exponents, the prime factorization for these integers are of the form 2 to the A1 times 3 to the A2 times 5 to the A3 times 7 to the A4. All right, so basically this is what we have done initially. This is our initial observation, and this is the starting point of our investigation in the relationship between Robin's criterion and the natural numbers themselves. So this was our starting point in our mathematical investigation. that was the preamble of our paper. Let's start with some initial consideration. Now, for an integer m, and given its compact factorization into primes, the values of sigma n are as follows. And you can see that I'm using already the map tau. So you can see the reason for introducing this notation tau. These relationships are given by Hardy and Wright on in their textbook on number theory. So again, it's taken as a given for brevity and conciseness. This remark is not proved. So we take it as given. Again, as an initial consideration, we define the map lambda for a prime b and any composite number m. We define lambda as follows: lambda of m times b. Okay, and then we manage to split this definition into cases, and show that this function lambda has some sort of multiplicative nature. So as you can see, the b comes out and there's a lambda m left in there, and then there's some additive residue over there in both cases. So this map lambda is important for our proof, and in the following section we show that lambda and the sum of divisor function are actually one and the same. And that's kind of like that is basically proving our statement. It's basically a huge step towards the proof of towards our global proof, our intention of showing that Robin's criterion holds. There's two lemmas, 16 and 17. Lemma 16 and lemma 17 are both concerned with divisibility by a prime, and they are used in further in the proofs of two other lemmas, namely 18 and 30. They are basic facts from number theory. Basically, what lemma 16 says, that if a prime b divides if a prime b divides a product of primes, then it must be one of them under some conditions. And if a prime b does not divide, what lemma 17 says, that if a prime b does not divide a product of primes, then it cannot be one of them, again under some conditions. This is I like these two lemmas very much, even though they're very simple facts, the very nice, very neat facts from number theory. Now lemma 18, if we let m be greater than the big threshold omega then that we have defined, we observe then that at least one of the following conditions holds. Then m is divisible either by 2 to the a, or 3 to the a, or 5 to the a, or 7 to the a, or b to the a for a prime b greater than 11. And in this lemma, in lemma 18, we let a be any exponent greater or equal to 1. Of course, integral exponent, so we're talking about natural numbers here, positive integers. All right. Again, a technical requirement. Now, lemma 19 states that the function phi is increasing, strictly increasing. Lemma 20 states that the function 1 plus 1 over n is strictly decreasing. Lemma 21 is concerned with Robin's inequality for primes greater than 11. And for a prime greater than 11, we show that sigma p is less than round phi of p. Lemma 22 is concerned with a lower bound for delta double logarithm of 2 to the a. We show that the lower bound in question is the integer 2. Lemma 23. So now we start getting into as before, as in the lemma 22, that was a lower bound. We start getting into some lower bounds. Lemma 23 is concerned with a lower bound for delta double logarithm of 3 to the a. The lower bound is in question is the rational value 3 over 2 or 1.5. Lemma 24 gives a lower bound for delta double logarithm of 5 to the a. The lower bound is in question is 5 divided by 4. Lemma 25 gives a lower bound for delta double logarithm of 7 to the a. The lower bound is in question is 7 divided by 6. Lemma 26 gives a lower bound for phi of b to the a for a prime b greater or equals to 11. And the lower bound in question is 11 divided by 10. These lemmas, these lemmas that deal with lower bounds, in particular 22 to 26, these lemmas are important for the base cases of our induction. Okay, now we move to the next section, which is inequalities and equivalences. We have 11 lemmas here, which are lemmas 27 to 37. All right. Lemma 27 gives an equivalence involving the sum of divisors and the map tau. Lemma 28 gives a relation between the maps tau and xi. Yeah. So again, in some conditions we can make use of tau and xi interchangeably. Lemma 29 provides an inequality. The inequality in question is q plus 1 phi, round phi of m is less than round phi of mq. This is for m and q greater or equal to 11. Okay, lemma 29 is a technical requirement and it is furtherly used in proving the results of lemmas 48, 49, 50, 51, 52, and 53. It is one of this lemma in particular is one of the important lemmas in our demonstration. The proof of lemma 29 follows after some algebraic manipulation, some inequality manipulation. It follows from lemma 20, which states that the function 1 plus 1 over n is decreasing. So in effect, that's all we need for proving lemma 29. As we have stated previously, we were going to prove an identification between sigma and big lambda. This is lemma 30, and this is actually the most important, probably the most important lemma in the entire paper. I'd say it's a very important lemma in this paper, because it allows us to use a different representation for the sum of divisors function, a representation which makes it easier to analyze what this sum of what sum of divisors is, and it makes it actually easier to perform it makes our induction attempt much easier. So for all m greater or equal than 2, we observe that sigma of m, the sum of divisors function of m, equals big lambda of m. All right. The proof of this result, the proof of lemma 13, proceeds by induction, and we use the result in lemma 17. Lemma 31 states that, lemma 31, again a technical requirement, b plus 1 times sigma m is less than round phi of mb for an odd prime b and m greater than 11. Again, a slightly technical requirement. Again, the proof is by the proof follows from lemma 20 and some rearrangement, some algebraic manipulation. Now lemmas 32 and 33 give an expression and an inequality respectively involving the function lambda. Lemma 32 gives an additive form for a portion. Remember, lambda is defined piecewise. So for one piece of lambda, we give an additive expression in lemma 32, and for lemma 33, we give an upper bound for again for the same piece in the piecewise definition of lambda. Okay, so these are lemmas 32 and lemma 33. Again, lemmas of a technical nature. Now, lemma 34 gives the inequality sigma of mb is strictly less than b plus 1 sigma m. This is in our overall proof. This is lemma 34 is very important. This is similar to the nail that basically nails our entire efforts. So it's lemma 34 is important. Now lemma 35 gives an expression involving sigma and xi. Again, sigma, the sum of divisors, and the function xi as defined by us may be used interchangeably under some conditions. Lemma 36 gives equivalences involving sigma, round phi, standard phi, and xi. So the two equivalences in questions are sigma of m less than round phi of m is equivalent to xi of m less than standard phi of m. And lemma 37 gives an inequality involving the map xi. Okay, so we're not going to insist. These are technical requirements. They are used furtherly in our proofs. In the next section, we take care of the induction in question, the induction on prime factorizations. And we let m be a positive integer and q be one of the following values. Remember, we have already seen these values. We have introduced these values in one of our earlier remarks. The values in questions are 2 to the a, 3 to the a, 5 to the a, 7 to the a, and b to the a for some values of a and b. So we prove in this section that if n is equal to m times q, then sigma, the sum of divisors applied to n, is less than round phi of n. Yeah. So this is overall. This is our overall results, and we make use of the previous results, the previous lemmas we have proved on previous sections. Okay. So given the prime factorization, m, the extended form of the factorization of m into prime, we prove by induction on the length k of this factorization that if sigma q is less than round phi of q and n equals m times q, then sigma n is less than round phi of n. These relations are proved in lemmas 38, 39, 40, 41, 42. The base cases are proved in lemmas 43, 44, 45, 46, and 48, while the full induction is proved in lemmas 49, 50, 51, 52, and 53. All right. Now, lemmas 38 to 42, as I have said, cover lemmas 48 to 32, cover some cover the inequality sigma of q less than round phi of q for some values of q and a, a being an exponent. This particular, so lemmas 38 to 42 are concerned with values of q that amount to a single prime raised to a given power a. So they serve as a base step for the induction in question. Remember, the induction is on the length of the prime factorization. So this is lemmas 38 to 42 are like a base step. The length of the induction in question is 1. Lemma 42 is again, lemma 42 is given there. Lemma 43, lemma 43 and lemma 44. Starting with lemma 43 and lemma 44, we begin to take q as we begin to take m. We begin to consider an integer m as a proper product. So we say m is q times b, where q is a given prime and b is any prime whatsoever greater than a certain threshold. And we do this in lemma 43, lemma 44, lemma 45, lemma 46, lemma 47, and of course, lemma 48. Okay, so up to lemma 48, we prove this. This is an intermediate step, and starting from lemma 49 and lemma 50, we prove that if n equals m times q, then sigma n is less than round phi of n, where q is a certain prime raised to a certain power, and m is any positive integer. So this we do this in lemma 49, lemma 50, lemma 51, 52, 53 as well. This amounts to the inductive step in our induction on structure. Now, the final section of our paper. Well, I think there are a few sections left, but the next section in our paper is Robin's condition holds, and we are able to prove that from two remarks we have discussed earlier. We know that if the value of the sum of divisors function sigma m exceeds that threshold there, e to the gamma m double logarithm of m, finitely many times, only then the Riemann hypothesis holds. Okay, so we prove in this section that the inequality sigma n less than e to the gamma n double logarithm of n holds for all n greater or equal to the big omega, the threshold that we have defined already. And it's greater than that threshold omega. Therefore, sigma n is greater than e to the gamma n log n only for a finite number of values for n. Hence, Robin's criterion holds, hence the Riemann hypothesis holds. So we managed to solve to give an answer in the positive for the Riemann hypothesis. Now, lemma 54 states that if n is greater than that big omega threshold, it can be written as a product of this form: n equals q times m for some n and q a power of a prime. This is very important, otherwise the induction carried previously would not apply, of course. Now, Theorem 55 asserts that if n is greater or equal to that threshold, the big omega threshold, then sigma n is less than round phi of n. While finally, Corollary 56, our final result, states that the sigma n is greater than e to the gamma n double logarithm of n for only a finite number of values for n. So, Corollary 56, sum of divisors function exceeds Robin's threshold for only a finite number of values for n. Okay, and in conclusion, for a positive integer n with n greater than big omega, we have proved that sigma n is less than round phi of n. It is easy to see that n is alpha n times beta n. Yes, we have defined these values in the beginning. Both alpha n and beta n are of integral value, and alpha n is greater than 11. We let m equals alpha n and q equals beta n, and for n equals m times q, we obtain from Theorem 55 that sigma n is less than round phi of n. And that's about it. this settles Robin's question. This settles the question of Robin's criterion and gives a proof in the affirmative, an answer in the affirmative for the Riemann hypothesis. Now, a little bit about myself, the author's biography. I was born in 1983, hence I'm 38 years old as it stands now, but that's in case someone may be interested of the fact that I am in fact less than 40. But that's less important. What is more important is that is my high school. It's in a small town, relatively small, in the western part of Romania. You can see the Romanian flag there. The name of the school was given after after our national poet, and a great what is relevant. What I'm not sure if people are familiar with this, but anybody that studies Romanian culture and Romanian literature will in fact find that a good portion, well, it's not the overwhelming portion of our themes, but a good portion of our thought is dedicated to expresses the idea that there exists a conspiracy against Romania, or there exists persecution against our nation, against Romanians and Romania in general. And this fact is incorrect as it stands. As a traveler as a traveler around the world, I have lived in 2 or 3 countries other than my native country, Romania. I also have double citizenship. I'm also a citizen of New Zealand. So as a traveler around the world, I noticed that there exists crimes against humanity in general. There exist crimes against the Celtic people in general. There exist crimes against black people. There exist crimes against Jewish people. There exist crimes against American people, against Africans. And I sincerely hope that this situation will come to an end sooner or later. Rather sooner than later. All right. And okay, so that's where I went to school, high school, in Petroșani, the west part of Romania. After maybe 6 to 8 months, I moved to New Zealand and I went to the University of Auckland. Well, I went to Massey University first in the North Shore of Auckland, but then I ended up at the University of Auckland studying computing, and I've graduated. I ended up doing half of my degree in computing, a quarter in philosophy, and a quarter in mathematics, and that was an interesting combination. All right, I've spent a great time I spent great time, yes, great both qualitatively and quantitatively, great time in North Shore in Auckland. That's where I used to work. It's a supermarket that's right behind the North Harbour Stadium. A wonderful place, an exciting place in Auckland, and that's Takapuna over there. I used to go there every week in order to buy Iron Maiden albums. I had all of their albums on CD at some particular point in time. We had a house in West Auckland, and I used to go to Piha a lot. New Zealand is a wonderful place, a slice of heaven. geographically, and a location for giants, politically speaking. And I hope New Zealand will continue, even though I'm not sure. I hear the situation has gone bad in New Zealand lately, or since I have left. However, I hope New Zealand will continue to be a great country globally, and New Zealand will continue providing giants in the big scale, the big scale that we call humanity, and the big scale that we call contributions towards humanity. I hope New Zealand will continue to be one of those places, the location for giants in general. And that is my alma mater, Victoria University of Wellington. It used to be called 60s, 70s, I believe. It used to be called the University of New Zealand. So this is equivalent to what in Australia we call the Australian National University. It is a great place for achievements. It is a great place for educational achievements in New Zealand. Probably the best, yes. And yes, I mean, I have seen stuff online about me. People have called me a professional student. This is incorrect. I used to work for, this is the place where I used to work as a junior computer person. I used to work for a franchise called the Australian Fast Foods, and this was in Perth, where I reside now in Western Australia. The Australian Fast Foods operate Red Rooster and some other restaurants, notably Oporto. Yes, Oporto is basically one of my favorite restaurants in Australia, and overall, I'd say one of my favorite fast foods. Yes, it's very good. Do try it. And I used to work as a consultant, as a software consultant in Perth for a company called Dialogue Information Technology. And I used to work as a first level technical support for a research institute called Teleton Kids. At the time when Teleton Kids was based in Subiaco. I think now it's based at Charles Gardner Hospital. And yes, I hope you enjoyed this presentation. I hope it's a step forward in knowledge. As far as I can see, the applications of my proof are purely of the interest for this paper is purely theoretical. Possibly people thought that the Riemann hypothesis had implications for cryptography, I think. Possibly. I mean, there is a question whether the distribution of prime numbers is random or not, which has implications for public key cryptography. However, the nature of my proof is plain, and but the nature of my proof is plain. However, I still hope it was enjoyable, and I hope it is a huge step for knowledge, and it's a huge step for mathematics. I entertain this hope. Let us part with this thought that this wish that I entertain to emancipate ourselves from mental slavery, for none but ourselves can free our minds. It is a quote from Bob Marley, his final song. The song goes saying that have no fear for atomic energy, for none of them can stop the time. I think we should not be fearful. I think a fearful attitude in life is damaging. So each of us either have something to be ashamed of, something that we've done in the past that we should be ashamed of, or we can look towards the past and hence towards the future with an innocent framework. And in the second case, in the case in which we are innocent, we know that there's nothing to be fearful of. We should live with our conscience. We should live with a clean conscience, and also act towards a better future for us, for ourselves, for our children, and for humanity in general.